Right after a brutal workout, you're usually not hungry at all. That's not just exhaustion talking. Scientists just identified the exact molecule your body fires off mid-workout that tells your brain, in no uncertain terms, to stop thinking about food. Think of it as a text message your muscles send straight to your brain. Every time you push hard enough to feel that burning sensation, your muscles dump lactate into your bloodstream, the classic muscle burn molecule. For decades, scientists assumed lactate was mostly just a waste product, a byproduct of muscles working without enough oxygen. A team at Stanford, led by biochemist Jonathan Long, went looking for anything unusual showing up in the blood right after intense exercise using a technique called mass spectrometry that scans for thousands of different molecules at once by their weight, then flags whichever ones spike hardest compared to a resting baseline. Out of that entire haystack, one molecule stood out from the noise, increasing more than almost anything else measured, in both exhausted mice and, eventually, in exhausted humans. Nobody knew what it was. Figuring that out is where the story actually starts. The unidentified spike carried a specific molecular weight, 236, and once the team worked out its structure, it turned out to be something built from two ordinary ingredients fused together. Lactate, that same muscle burn molecule, chemically bonded to phenylalanine, one of the amino acids your body gets from protein. They named it Lac-Phe, short for N-lactoyl phenylalanine, and published the discovery in the journal Nature in June 2022, with Veronica Lee and Yang He as co-first authors on the paper. Here's the text message layer that makes it interesting. Lac-Phe doesn't get made everywhere lactate shows up. It's manufactured by a specific enzyme called CNDP2, which normally does a completely different job breaking down other small proteins, but under the right chemical conditions runs that reaction backward, welding lactate and phenylalanine together instead. That enzyme turns out to be concentrated in immune and epithelial cells tucked into organs throughout the body, not, as you might assume, mainly by muscle cells themselves. And in a detail Long has described in more recent interviews, a major source turns out to be intestinal cells lining your gut, meaning part of this signal is quite literally a gut-to-brain text, not a muscle-to-brain one. So what does the text actually say? To find out, the team injected Lac-Phe into obese mice and watched what happened. The mice ate less, essentially immediately, within 30 minutes of the injection. Crucially, when the researchers checked whether the mice were simply moving around more or burning extra calories, they weren't. Oxygen consumption, carbon dioxide output, and general activity levels all stayed the same in metabolic chambers built to track exactly that. This wasn't a metabolism boost. It was a hunger switch being flipped off, cleanly, without any of the jitteriness or restlessness you'd expect from a stimulant. Keep the treatment going for 10 days, and the mice's body weight and fat mass both dropped, along with meaningful improvements in blood sugar control. Then the team ran the experiment in reverse. They bred mice genetically unable to produce Lac-Phe at all by deleting the CNDP2 gene and put them through a regular exercise training program. Normal mice that exercise regularly eat less and stay leaner as a result. The Lac-Phe deficient mice didn't get that benefit at all. Despite running just as much, they ate more and gained more fat than exercising mice that still had the gene intact. Take away the text message, and exercise loses one of its biggest metabolic payoffs, even though the physical activity itself hasn't changed one bit. That's airtight mouse biology. The human side of the story is real too, just built differently. Blood drawn from 36 people before and after a single treadmill run showed the same molecular signature climbing sharply, and so did blood drawn from thoroughbred racehorses immediately after a race. This signal turns out to be conserved not just across mice and humans, but across mammals generally, wired into muscle physiology that predates any of us. A separate group of 8 people each completed 3 different types of workouts on different days: sprinting, resistance training, and steady endurance exercise. So researchers could compare all 3 head-to-head within the exact same bodies rather than across different groups of people. Sprinting produced by far the largest spike of the 3. Long himself has pointed to lactate as the reason. The harder and more explosively you push, the more lactate floods your system, and Lac-Phe production follows lactate's lead almost step for step. So sprinting wins the race to spike this particular molecule fastest and hardest in a single acute session. But spiking a molecule for a few intense minutes and using it to actually shed body fat over the following weeks are 2 different questions. And only one of those 2 questions has actually been tested directly in real people over time. No published trial has ever administered Lac-Phe to a human being, and no trial has tracked whether sprint training specifically converts that big acute spike into real measured fat loss over time. The only study that has actually connected this molecule to real human body fat, published in the journal Metabolites in 2023 by a University of Tübingen team led by Miriam Hohn, followed 22 sedentary adults with overweight or obesity through an 8-week supervised exercise program. And it used endurance training, 30 minutes of cycling and 30 minutes of walking, 3 times a week, not sprinting, using MRI to precisely measure fat volume before and after. The researchers found that people whose Lac-Phe spiked higher after each endurance session lost significantly more abdominal subcutaneous fat over those 8 weeks, an association that held up even after accounting for age, sex, and how much muscle they'd gained. Visceral fat, the more dangerous fat surrounding internal organs, showed the same direction of effect, just a weaker one. The molecule that sprinting spikes hardest in a single session is the exact molecule that, in the one real-world human weight loss study on record, was proven out through steady endurance work instead. The appetite-suppressing, fat-reducing biology behind Lac-Phe is proven, right down to the exact gene that makes it work. That part rests on solid mouse experiments, cause and effect, not just correlation. The human proof of concept for turning this molecule into actual fat loss is real too, just built on endurance training, the modality nobody expected to be first across the finish line here. Sprinting may well turn out to do the same or more. That specific trial simply hasn't been run yet, and until someone runs it, that gap stays open. What already holds up either way? Your body sends a real, measurable chemical signal to your brain after a hard workout, and that signal is a meaningful part of why intense exercise leaves people less interested in food afterward, not more. Next time a workout kills your appetite for the rest of the afternoon, that's not just willpower or exhaustion talking. Somewhere in your bloodstream, a text message already got sent, and your brain already read it.